thanks a lot, Paul, for inviting me to speak here. Let's talk about I want to start with a little bit of just general motivation, and then I'm going to really try to do something like a mini course where I try to actually prove something a little bit. So X omega is symplectic manifold, dimension n, and then J is an almost complex structure, which is omega compatible or omega tame. And what is open Gromov-Witten theory? So is I forgot. Yeah. So is when you consider inside of this guy a Lagrangian submanifold, and you're interested in counting so let's talk about genus 0 only. So we want to count maps. This is not enough room. So we have a Lagrangian submanifold here, and then L, and the whole blackboard is X, and then we have a disk over here, and we want maps from the disk into the Lagrangian into the symplectic manifold, which map the boundary of the disk onto the Lagrangian submanifold, and these maps should be J holomorphic. So I'll call this U. So U maps the disk relative to its boundary to symplectic manifold relative to the Lagrangian. And it has to be J holomorphic, so like that. And in general, this is the moduli space of such maps is going to be a finite dimensional something or other, and we want to make it into a zero dimensional something or other so we can count it. And whatever it is, it's definitely going to be compact. So the way to make it zero dimensional is we impose some constraints. So there's different kinds of constraints we can impose. One version would be to constrain the boundary. So say P1 up to Pk. That's boundary constraints, and then not enough colors. That distinguishable, yeah. And then say Q1 up to QL. Interior constraints, so think of P1 Pk. They're sort of chains on L, or I would, well, I mean, in the most well, in the naive version, you want to look at cycles, but that's going to turn out to be the wrong thing to do. Cycles on L in some cohomology theory. Eventually, we'll look at differential forms, but so far, just anything you want. And Q1 to QL are cycles on X. And if we choose the number of constraints and their degrees and so on properly, so we also want to, of course, fix U star of the fundamental class is equal to beta of H2 XL. So if we choose the number of constraints and the degrees appropriately with respect to this beta, then we'll get a zero-dimensional moduli space, and we should be able to count things. So here's an example of something which was done in this direction. So this is, I guess, Welschinger, show myself, years, say, between 2003 and 2006 in various different forms and levels of generality. And so I mean, the point is that you'd like to do this, but you can't really do this because the count is not going to be well defined. So I'm going to just write down an example of when the count is well defined, and then just sort of start staring at this and looking at all these conditions which come up to make it well defined, and then sort of ask a bunch of questions. So first, like one condition is suppose that n is equal to 2 or 3, and there exists a antisymplectic involution of x with the Lagrangian fixed by this antisymplectic involution, right? Sorry, I forgot to say it's an involution, and I forgot to say it's antisymplectic, and we have to assume that everything else is kind of preserved by this involution, and Qj equals this minus Qj, and anything else that I have to assume here? Yeah, maybe we should say that the dimension of Qj is even, or whatever, the degree Qj is even. And let's, it depends on the degree. -1 to the degree. -1 to half the degree. And so I'm going to just ignore signs throughout today's talk, just absolutely, and they're all going to be depending on everything in sight, and I'm going to do it next time as well. But all the signs are written in gory detail in the archive preprints posted a few months ago. So, and of course in the original things many years ago. Right, and another assumption is going to be that, let's just assume that all the Pj, all these boundary constraints, and Pj are all points. All right, so in this case, then OGW beta k of Q1 up to QL, which is going to just be the sum, or the number, I should say, counted with appropriate signs, of course, of u as above, so u is in the picture, is well defined. So depends only on, it only depends on the homology class of this cycle in, say, and that doesn't depend on in general, maybe a rational number. So I mean, in general, like there might be some kind of automorphisms here, but like if your manifold is sufficiently positive, you get an integer. So like for projective space or something like that, if you normalize things correctly. So it doesn't depend on J or the choice of the P1 through Pk. And is kind of a deformation invariant of phi and omega.
So can I ask a stupid question?
Yeah.
So to what extent is this a theorem in algebra? In the sense that to what extent can you recover this number by just saying in this setup you have an A-infinity algebra?
That's what we're going to talk about.
Very good.
Okay, so a priori this is just kind of like some kind of crazy million conditions, which, I mean, let's just try to like a few of the things which for me are like most bothersome about this theorem. So actually, before I do that, I should just mention that there's yeah, so wait a little bit. So you can remove some of these conditions. So you can allow an odd, arbitrary, but then you have to take k has to be 0, so no boundary constraints. And then also you have to say that the dimension of Qj has to be equal to sort of 2 mod 4. Okay, so this is like another sort of strange thing that happens, and so you can kind of trade some conditions for stronger conditions on other things. All right, so well, maybe she only considers the final case in some sense for technical reasons, and therefore it's Z or something. But I think so a bunch of questions. First of all, why n equals 2 or 3? So what's special about those dimensions? Second of all, so why do we need phi, this anti-symplectic involution?
Sorry, when you said degree, now you said dimension. So is the question of dimension versus co-dimension, or degree of Qj is even?
But here I'm saying that it's actually got to be equal to 2 mod 4, which is a further constraint.
But what's the difference between dimension?
Oh, sorry. Yeah, I was just being inconsistent. Degree.
Is it the actual dimension of the cycle, or is it the co-dimension? Now it matters.
Now it matters. Yeah, and here it is the. This was supposed to be the dimension. But I could have said it as the. No.
No, it's okay.
Sorry. It's actually the degree. The degree means the cohomological degree.
Co-dimension.
Codimension, yes. So we should really say codimension. Yeah, codimension. How about that? That's even more. Yeah, maybe that's just like the clearest way of saying it. Codimension of Qj is 2 mod 4. Okay, and y need phi and y are p1 to pk points. So in general, you could imagine sort of counting holomorphic disks which pass through a whole bunch of different constraints, constraints on x and constraints on L, but somehow in the examples that we know, what comes up is just point constraints on L. And you can have other kinds of constraints elsewhere, in x, I mean. All right, so we want to try to explain these 3 questions. That's the goal of these talks. And I just want to give a little. So what can you actually do? Last. Oh. So theorem. This is Sartor-Koczynski on the archives of this summer, at least the first parts. So first of all, we can so there's going to be 2 different possibilities here. One of them is that we can even drop the antisymplectic involution entirely. But then we have to assume a fairly strong condition on
K is still the number of points boundary constraints.
Yes, K is always going to be, unless I make a mistake, the number of boundary constraints throughout.
Which are all points.
Which, in all the theorems I'm going to say anytime, are always going to be points. And that's why I don't have to say what they are, because they can only be points. So that's why I put them as a subscript. Thanks. So one thing I can do is assume that I have a sort of real cohomology sphere, which is a kind of condition which, for people who are familiar with Floer theory, makes you think about vanishing obstructions. And that's exactly what it is. Or B, yes, you have phi, but then, so here, n can be odd, but that's just sort of an inessential technicality. Sorry?
What you just said about unobstructed and so on.
Yeah.
That assumes n is odd. If you had a 4-dimensional sphere.
Well, I don't know. Sort of. The main problem here when n is even is that then the signs become much more complicated because you have to allow some things in your Nova covering which have odd degree, which is a pain. So then we can weaken the assumption on the cohomology and say instead that the cohomology of L agrees with the cohomology of the sphere, but only in certain only for certain degrees. Say Q equals 0 or 3 mod 4. So yeah. So I think what's nice to say, just the moment you see this, what you want to do is say okay, so how does this relate to what we had before? And I think the point here is that, say for example, this condition B is automatically satisfied if the dimension is 3. So in other words, once you have like an antisymplectic involution, then somehow, if you're in low dimensions, then just by sort of because the cohomology of a three-dimensional manifold is concentrated in degrees between 0 and 3, and Poincare duality says it has to be like a sphere in degrees 0 and 3, then sort of there's no obstructions left as soon as you have this involution. So basically, the involution we can see already here, as well as the dimension, are playing a role in causing some obstructions to vanish. Yeah.
So if I had a Lagrangian three-sphere and a Calabi-Yau threefold,
Yeah.
then yes.
Yeah. But see, then it would be, well, so that's probably like not the example I would want to think about because
I mean, in that example, there is a J which all its Euler spaces are below something.
right, so that's one problem. So first of all, you can get rid of all the disks by stretching the neck a bit by a theorem of Mohammed and Welschinger. But that's not really kind of the last word because then you'd create some spheres and there's probably like a non-trivial invariant there, but
when you said you can define
covered here.
it's an invariant. It's a special case of case A.
it will be 0.
Zero.
The things I'm talking about today will be 0. There's other things which are a little bit better which are not 0, perhaps.
RP3 is maybe the best like that.
Okay, so
But what it means is that you could have a sphere and there could be a single disk attached to it and it could be irregular and your invariant would say this is 0.
that's right. I mean, because I'm going to throw out some stuff which is an invariant today. And so there's, I think, maybe Sarah's going to visit in the beginning of February, and then maybe she's going to talk about what's not perhaps 0 for that, but which is kind of something which combines spheres and disks in an appropriate way. But today I'm going to just stick to
Okay, so maybe this should be on the board that for a sphere in a Calabi-Yau threefold is over 0.
okay.
This is somewhat unexpected.
Well, I mean, this issue that you can stretch the neck and get rid of all the disks is kind of makes it so that you really wouldn't expect to get anything for a Lagrangian three-sphere and a Calabi-Yau manifold, or at least I never expected to get anything.
But the equally plausible argument is that if you have a single disk and it's regular, you should get 1. If it's supposed to count them, right?
Okay. That's reasonable. Okay. Will vanish for Lagrangian
Did you also say that it will always vanish, or
will always vanish?
you didn't
Oh no. Okay, I'm gonna allay these fears in just a second. Okay.
By the way, under B, when you say automatic, is it automatic that the Lagrangian is orientable?
Sorry, I should have said that L is orientable in this theorem. Yeah, I forgot that sometimes it's not, and yeah, spin or relative spin is enough. Here we actually have to have spin, honestly spin, otherwise things get evil. And Yeah, maybe n has to be 3 mod 4 here. Again, for some kind of for obstruction reasons. Okay, sorry. All right. So part 2 is that these invariants. So they're going to be well defined when n equals 3, or they're going to be no, but you can, if you fix an energy level, then you can kill all of them. So the second thing is that these invariants they coincide with the ones from the theorem 1 and theorem 2, when both are defined. And 3 is that they satisfy some axioms, sort of like the Gromov-Witten axioms, sort of. In particular, you get sort of a WdVV equation. And this allows you to compute the invariance for, say, XL. So we can compute just all the invariants for XL is equal to CPN, RPN. And there's a lot of different choices. And kind of, various enumerative and non-enumerative interpretations. So, example, just want to fix the first case, which it doesn't fall into any of the previous theorems. Say n equals 5 and XL is equal to, I just said CP5, RP5. Let's suppose that we don't have any interior constraints. So just L is always going to be the number of interior constraints is 0. And now we can just do a little table. So then we can look at the degree. So beta. Right. So in this case, the second homology is equal to the integers. And so just our degree is going to be just a number, and we look at just various degrees. 1, let's go 1, 5, 9, 13, 17. Okay, and then we'll look at the number of boundary mark points. 2, 8, 14, 20, 26. So I'm just going to look at all the non-trivial invariants for which only involve boundary points. But then, of course, if you start sticking in interior constraints, then there's going to be sort of a huge number of different possibilities, and it's going to be hard to put in the table, so we're not going to do it. OGW beta k. So for the degree 1, so this is like the number of lines between 2 points, essentially. And the number is 2 because there's an orientation involved, because you look at the disk, induce an orientation on the boundary. Number of oriented lines through 2 points. Okay, in degree 5, we get minus 2. This is kind of like the oriented rational normal curve. So basically some kind of linear algebra, which you can look at curves of this degree n in dimension n. And then comes the funner part, more fun part. So when you go to degree 9, you get 1974. I don't know what that means in classical and enumerative geometry. And degree 13, we get 42,781,410. And in degree 17, we get 7,726,794,150. And we can go on and on. Right, so indeed for spheres and Calabi-Yau manifolds, these are not so interesting. For RP3s and Calabi-Yau manifolds, you know, they are interesting. So this is only like real homology. So okay, so what's the idea? So why aren't disk counts naively invariant? So what can happen is you can be counting a disk and then say change j. So let's just think about boundary constraints from now on. So we have, say, a whole bunch of boundary constraints, p1 to pk. And then we can say change something, like say change one of these constraints, or change j. And then what can happen is that this disk can start to bubble, start to sort of pinch, and then continue changing, and it will develop a node. And finally, it just disappears. And then you're counting 1, and afterwards you're counting 0, and therefore it is not invariant. So the idea.
It doesn't. I mean, in that homology class, it disappears, right?
Yeah, and that's So I'm going to just say in a second that it. Right, the two pieces are now going to start moving around, and you want to somehow keep track. Right, so I mean, yeah, maybe Paul was saying I should draw this picture instead. So this is kind of like in parentheses. But there, yeah. A priori, it's not so clear how to count, you know. Sorry?
So initially you start with some problem that has expected dimension.
0. Exactly. So this doesn't have expected dimension 0.
Okay.
So it's not even clear how. That's like first thing perfect. Yeah. So it's not really clear. You know, this is expected dimension 0, but as soon as you remove this nodal condition, you get something which is not expected dimension 0. And how do you count that? Okay. So the idea is that, and this is kind of an idea which has been around for quite a long time, but it's somehow not entirely straightforward to see how to apply it to solving an enumerative problem because of stuff I'm going to say. So the idea is, instead of like continuing to the empty set, you want to continue to a situation where you have where you count something like this, where now you have two disks which are separate, and you still have some constraints over here. Whatever. And then you sort of want to instead, so you have some sort of additional constraint, which is that this is, call it B, which is a chain on L such that the boundary of B is equal to sort of like all points on the boundary of a disk like this. Okay, so what I mean here is just what exactly what Elsa was saying, is that this disk, once you remove this nodal sort of constraint that the two disks intersect, then either side is going to be actually a higher dimensional moduli space of disks. And so I'm just drawing a single disk here, but in fact you have like a big family of disks, which could be, for that matter, filling up your entire Lagrangian. And then, but it could also be some kind of middle dimensional cycle. And then you want to choose some sort of chain on L, which has its boundary equal to all the points on the boundary of all possible disks passing through the constraints on, say, one side of this bubbled thing. Okay, and this is a great idea, but of course you have to do things symmetrically. You can't just count the B on this side. You could have to count it also on this side. So you want to sort of so you need to sort of do this so symmetrically, and you have to okay, so I'm not sure that it's entirely clear what I'm drawing here, just for the people who don't already know this. So what's happening in this picture is that sort of so just imagine that at some point I had a disk which was sort of down here, but then as I changed J further and these disks moved apart, this nodal disk sort of split. And what happens is sort of like this disks no longer intersects each other, but it sort of like moves, it slides up this sort of red chain B, which is the bounding chain, which will be called the bounding chain at some point. And then you want to just keep track of, so instead of like the movie ending when the disk degenerates, it continues by the sort of disk sliding up the bounding chain for the other disk. And you have to symmetrize this, of course. And you also have to do this recursively. Okay, so like you have this disk which splits into two disks, and then this is kind of like the two disks. Okay, and then like as you further change J, so you have like a one, as J changes, you're going to still have like for each value of J, there's going to be a disk which is going to sort of gradually work its way in. So it's going to, at the beginning, it's going to be intersecting the boundary of this chain because it's going to be intersecting a disk. But then as J continues to change, it's going to work its way into the inside. It's going to sort of like slide up this bounding chain and get up to here, which is like some random J. That's what I was saying, sort of. So this is, continue to change J.
case because there's no other way to do it.
Yeah, absolutely. I
Two
mean,
disks, there's no way to say this is the first. This
of
is
course, yeah. So, I mean, you have absolutely no choice but to do this symmetrically, and you have no choice but to do this recursively, because of course, there's nothing which says that you keep on changing j, and this guy might split. So then, and for that matter, this one might split. And so then you have to keep on doing this until the entire depth, which has something to do with the degree of your disk. And third of all, you have to sort of keep track of all the choices you made. Since when you choose this bounding chain, when you choose this bounding chain, I mean, there's a huge number of possible. You just some chain on L, which is boundary is determined. You could have chosen anything. There's a huge choice there, and you just have to keep track of all of them. And this is one reason one might want to study A-infinity algebras. So these three requirements lead us to A-infinity algebras.
So can I ask a very specific question?
Yeah.
So why can't I just add more marked points in the boundary and take the fiber product? You're saying this is another possible result you get after gluing?
OK, so if you just sort of look at the compactification, you're saying I don't look at anything like this, right? So just suppose I look at this thing. So then actually you would just get the empty set. So unlike in the algebraic case, so in the algebraic case, sort of this sort of degeneration is codimension 2. And so I mean, you can smooth it in many different ways. So if you kind of come into this degeneration from one direction, you can smooth it out in another direction and go right out. OK, but in this case, sort of the analysis of gluing disks shows you that there's only one way to smooth a disk. So if you came into a disk as you moved along, there's, after that point where you split, you go to the boundary of the moduli space. In general, you expect there to be nothing more after that point in that moduli space of disks, stable disks of a given degree. So in algebraic geometry, the moduli space is a closed orbifold. In this setting, the moduli space is going to be an orbifold with corners. So you can just think that, just think of manifold with boundary. OK, so this corresponds to sort of you have our moduli space of m x k xl beta k whatever. This is our moduli space, and then we're sort of this disk is like a point in the moduli space. And as you move along, it sort of moves towards the boundary, and then at some point it's on the boundary. And then at some point, it's just fallen off the boundary. This is something which doesn't happen in algebraic geometry, because then the moduli spaces have no boundary. Does that answer your question?
But if in the zero-dimensional case, then I don't expect any boundary.
No, but the question is when you vary the almost complete structure, right? So if you're counting something, the parameter
I see.
is going to be
so
one-dimensional.
Independence.
Yes,
with
and
respect to
exactly.
It just ends at some point.
It ends at some point.
Or even suppose that you're talking about fixing the complex structure and varying the p's.
Yes.
OK, so then you'll have this point is going to move around in the moduli space as you vary the p's. And at some point, it could just move and fall off the boundary.
Okay.
And then we're saying, well, maybe we should look for some other moduli space, which can kind of sort of glue onto the boundary of this moduli space. And then another moduli space which glue on the boundary of that moduli space, and another one which glue on the boundary. And at some point, you get something which is hopefully invariant. But we have to do this very systematically, otherwise we won't get anything which is even well defined.
Is there clarity on this point?
Good. All right. So A-infinity algebras, from my perspective, is just So this is just a way of encoding the Gromov compactness theorem in an algebraic gadget. Yeah. And it just, somehow in much of the literature this becomes rather technical, and I just want to, in a few minutes, try to convince people that this can be done, at least in some settings, with very, very little technicality and in a sort of transparent way, and differential forms. So, and the next time I'm going to talk more about how you start from an A infinity algebra and then go to a number or a series of numbers. So. Right, so I just have to do a little bit of notation before I get started. So as usual, I need to look at a Novikov ring. So this is going to be the set of all formal sums, a, I, t to the beta I, where a, I, just real numbers, and So t, say pi, is going to just be sort of like h2 xl divided by some subgroup. I haven't used it yet. And this subgroup has to be contained in sort of like the kernel of the symplectic form. So symplectic form defines a homomorphism on h2 relative h2, so that we have to be in the kernel of the symplectic form and in the kernel of the Maslov class. So and this is like the Maslov class. So mu h2 xl goes to z is the Maslov index. Okay, and so you could choose many different things for this G, and I'm often just nice to consider G the trivial subgroup. But if we want to see how obstructions come in, then sometimes they involve phi. It's nice to take G a little bit bigger than that. So we can take AI to be real numbers, and beta I are just some elements of pi, and we just need to say that omega of beta I goes to infinity as I goes to infinity. And I guess I want to say that is also always greater than equal to 0. So this is a kind of a Novikov ring.
Okay, so this is lambda greater equal to 0?
Yeah.
Lambda plus or something.
Okay, and so this is the Novikov ring, not the Novikov field. So I'm just saying in a sort of confusing way to take a certain completion of the group ring of pi, of like part of the group ring of pi, which comes to a sort of like.
It's like a sub-monoid of the group ring.
Exactly, it's like a you take a sub-monoid in pi and then take its group ring. T beta is just like a symbol, right? So t beta 1 times t beta 2 is equal to t beta 1 plus beta 2. So like these are just some sort of formal symbols, like notation for the group ring, such that they satisfy this algebraic relation. And now I'm going to look at just differential forms on L. And we want to define some algebraic operations on these differential forms. So we need to use this moduli space. Well, I'm going to just drop this bar because it's always going to be compactified. So we're going to look at just sort of maps from the disk to XL, which are J-holomorphic, and which represent the class beta. So beta here is in pi. So I can talk about just the class being in pi. Just take the equivalence class under the quotient map, and so U star of the fundamental class of the disk is equal to beta. And then we also need to have sort of Z1 to Z0 to Zk. They have to be in the boundary of the disk, and then they have to be pairwise disjoint. And then, sorry?
Not in cyclic order.
And they are in cyclic order. Sorry. So cyclically ordered, with respect to the orientation on the boundary of the disk. So the orientation on like this thing induced by the complex orientation on the disk itself. The orientation on the boundary of the disk induced by the complex orientation on the disk itself. Okay, and of course, we also want to take the sort of stable map compactification of this guy. And I should have said also that we, of course, want to sort of divide this thing out by automorphisms, which is going to just be PSL2R, basically. And so let's focus on, say, the case when XL is a homogeneous space. I mean, so if we don't want to use all kinds of virtual techniques, then it's helpful to just look at the homogeneous space case. So simplifying assumption, say XL sort of homogeneous. So for example, CP and RPN. I don't want to say the exact things because I don't have much time. Exact requirements. Basically, you have to have a large group action, which still remains large enough when you look at just a subgroup which preserves the Lagrangian. And so then, oh yeah, I forgot to say, we have from here maps to L called Fj, and this takes some pair UZ and maps it to U of Jz. So you have all these marked points on the boundary of the disk, and you can just look at the map U and evaluate it at this marked point Zj, and so so the fact is going to be that mk plus 1 x L beta is going to be a smooth orbifold and it's also going to be compact. Sorry. All right. And now what we want to do is define.
I mean, with a nice compactification.
I've compactified.
Ah, okay, sorry.
kind of. All right, and we'll talk about the compactification because, yeah. So this is sort of like very similar to the case of like a convex algebraic variety. So then, in the early days of Gromov-Witten theory, people were looking at, Gromov-Witten theory of projective spaces and Grassmannians and flag varieties, and they didn't have to worry about even the algebraic virtual moduli cycle because they were willing to just look at these homogeneous spaces, and they still have kind of, fairly involved Gromov-Witten theory, and you can have lots of fun with fairly basic tools. So we define MK. We're going to map a. So we want to look at coefficients in the Novikov ring. So these are differential forms with coefficients in the Novikov ring. And I'm going to map this thing to the kth power to this thing itself. K here is going to go from 0 up to, to whatever. And it's going to be defined by just this thing. Is equal to the sum over k of t, sum over, what am I talking about? Beta in pi of t to the beta, and now we do this has to be an additional decoration here for the notation to make sense. So the evaluation maps are going to be labeled by the degree of the moduli space, and this will make notation unambiguous. And then we have set this mk, say alpha 1 up to alpha k, which are going to be differential forms with coefficients in the Novikov ring. We're going to just pull back the first one, wedge it with all the other ones, pulled back by the appropriate evaluation maps, and then sum over beta. And we're going to add a little correction term, which is just that when k is equal to 1, we'll add the exterior differential. This is just the exterior differential.
So what if I said I don't know how to push forward differential forms?
OK, so I'm going to talk about pushing forward differential forms. This just means integration over the fiber. But I'm not going to stop here. Because I'm supposed to really give a mini course, so there's going to be some kind of proof of something. OK, so what we want to prove is that, so maybe it's a good idea to just draw a picture of this thing for the non-experts. So the picture is something like you have a lot of P1 up to pk, and sorry, what am I talking about? These are not p's anymore, they're alphas. Alpha 1 up to alpha k. So we just think about differential forms as being some kind of Poincare dual. So imagine the differential form had a Poincare dual. It doesn't, because Poincare duality applies to slightly more restricted objects, but just imagine the differential form is something like the geometric cycle sitting inside of L. So this is kind of Poincare dual to alpha 1. Right? So we think of as looking at all the disks. So this thing is sort of like okay, let me just be a little bit more concrete here. So this is going to be, I'm going to just write this as sum of m k beta t to the beta. So this is the way of defining mk beta. I'm going to break down the mk into a bunch of little summands, which remember the degree of the maps involved. So sort of this is defined by this equality. So just look at the coefficient of t to the beta, and here you get mk beta. And I'm going to draw mk beta. So mk beta of all these guys, mk beta of alpha 1 up to alpha k is basically going to just be like all points which could possibly lie on a disk which passes through alpha 1 up to alpha k. All points, yeah, the chain given by all points that lie on a disk through alpha 1 up to alpha k of degree beta. So a disk of degree beta.
Jake,
Yes?
you said integration over the fiber,
Yeah.
and now you switch to cycles.
Right, so I'm going to always be imagining cycles Poincare dual to my differential forms, which is a really evil thing to do, which is imagine that somehow.
Well, but I mean, imagination is one thing, but you wrote down something.
So you want me to say what the integration of the fiber means? Or
Usually it says why it works here.
why it works?
Here.
Okay, so I mean,
This set.
right, I should have said, okay, it's a smooth overflow of the corners, and the evaluation map is a submersion. I forgot to add. And
Still
being
confused.
compact, it's proper.
I'm actually still confused. So if you had, suppose I had, a disk
Yeah.
lying inside a sphere.
Mm-hmm.
So that inclusion is a submersion. Right?
Yeah.
It's a manifold with corners. What?
It's not
Yeah, that's a perfectly good submersion.
A disk sitting inside a sphere.
okay.
What?
Fine, keep going.
I mean, because it's got boundary and corners, right?
Yeah, but
What's gonna, but then if I take a differential form on the disk and I push it forward, it's definitely not a differential form on the sphere.
yeah, but that's because the boundary is living in this case the boundary is living in the fibers of the
Okay,
maps.
so it's not just a submersion, but it's on each stratum it's a submersion.
That's why it was objecting. Yeah, sure.
Yeah, so you are objecting to my definition of
Submersion of manifold with boundary onto something.
Okay.
Yes. I mean, in our case, in fact, from each possible moduli space and each possible stratum of each possible moduli, it's going to be a submersion. So, right. So what we mean here is just, all right, I don't have so much time here, but so what I was going to try to, like lemma or whatever, really long and annoying lemma to prove, but actually kind of cool, is that, m k1.
And also, the point you say on the boundary it's not the whole one because you want to order it.
Yes, thank you. Changing all points that lie on a disk through lie at position 0, like
Between alpha 1 and alpha k.
between z1, zk, and z1.
What if it's case 2?
It's fine. You know which side.
According to the cyclic ordering. That's what we're always like saying throughout, yeah? So, so we want to say this lemma is that the A infinity stuff is satisfied. Yeah, so again, plus minus, where plus minus depends on everything in sight. And this is the A infinity relations. Okay, I don't have as much time as I hoped. I do have much time. I do have time on Friday, but let me just say what goes into proving this theorem. Essentially, you want to use 5 or whatever, this pre-lemma. So properties of integration or push forward. Okay, so I want to claim that even at this level, this is a completely algebraic thing. Just like you can just use sort of so let's suppose that f from m to n is a proper submersion. And so like its relative dimension is S, which is equal to the dimension of m minus the dimension of n. Okay. Then there's a map f star from differential forms on m to differential forms on n, shifted by minus s, and satisfies, and is actually defined by, uniquely defined by the following 5 properties. Okay, so first of all, if n is equal to a point, then f star of alpha is equal to the integral over alpha over m. Okay, so it's a generalization of the usual integral. Second of all, it's kind of functorial in some sense. F star, so if G maps from n to p is also a proper submersion.
That's a stupid question. Does that require orienting?
Yeah, everything is oriented here. I'm ignoring signs in this entire lecture. I already announced it like 20 times. I mean,
You can't integrate at all with that.
It's fine, it's fine, it's fine.
you want me to put in the signs? Here you go.
I just wanted that you should say the map is wrong.
If you want to talk about relatively oriented maps, I'll do that too if you wish.
Just say
Okay, so proper submersion. Then sort of like G star of f star of alpha is equal to G composed with f star of alpha. 3. So this is this is like a generalization of what's known as Fubini's theorem. So the proofs of all these things are completely elementary. absolutely seriously. And third, then if so now we have like f of f upper star of alpha wedge beta, right, is equal to alpha wedge f lower star beta. Okay, so this is an example. This is a generalization of the fact that integration is linear. Integration is kind of like R linear. And here you have like sort of, you work over some it's linear over differential forms on the base. And now here we can look at if, right, if we have like a Cartesian square, which is like m goes to n, and p and q. So let's suppose this is I say q is equal to, this is like a proper submersion. So that means that this pullback is well defined. Then q is the fiber product. And what I'm saying here depends on a certain orientation convention for fiber products, but it's still true. And I suppose we have now like P, Q, F, G. Then we have that if we push forward and pull back, then we get the same thing as pulling back and pushing forward. This is thought of as a sort of a version of change of variables. And finally, there's the Stokes theorem, which I must lecture on in exactly a half an hour from now, which is that if we take the differential of the push forward, then it commutes with the differential. But there's a correction term which comes from the fiber-wise boundary. So I'll write this sign here just for kicks. So here this is the fiber-wise boundary. So you only look at the boundary which kind of which lives over the interior kind of M. So M and N could both have boundary and corners and all this junk. And T here is right here, alpha is now, for this sign to be uniform, has to be in of degree T. So this is Stokes' theorem. Okay, and I claim that these 5 properties completely formally, combined with what we know about the structure of the boundary of M, lead to the infinity relations. So
So is there a claim that this is new? I mean,
this is completely classical. This has been known since like the time of Poincaré. And
I mean, this I know, so I'm sure for what's the...
there's absolutely nothing new. I'm just giving an expository lecture on A infinity algebras. But just, I think again, most of Fukai's paper, everything is written for like assuming maximal generality and using virtual fundamental classes and so on and so forth. Whereas here I'm saying that you can get away with using absolutely minimal technology, and basically you can write up in 100% complete detail a construction of A infinity algebras and proof of this equation and many, many other properties in 30 pages.
Including the smooth structure on the modular
No.
space?
But I mean, this is something which is kind of, which is, in a sense, contained in, algebraic geometry papers from 1994 or something like that. Because you get, like, suppose you want to look at the case where X and L are like, L is the real locus of some algebraic variety, then you can really just take that smooth structure and sort of do some fairly elementary operations on it, and looking at fixed points of an involution, which anti-holomorphic involution, and then you get a smooth. You have to cut it apart a little bit, and which is again something which is completely sort of elementary to do for a smooth orbifold with a normal crossings divisor in it.
I have a suggestion. Since we seem to be converging towards discussion, I think we should leave how it follows from axioms 1 to 5.
Yeah, I'm not going to say that.
And just ask for questions. It seems like a good idea.
Question.